In this section, we will discuss about pH titration and also solubility problems. Now, we begin with a strong acid, a strong base titration. So basically, you're adding NaOH to a solution of HCl, and at the same time, you keep track of how pH is changing. Since initially we had all HCl, so pH was less than 7, and that's why we begin here. So pH was less than 7, then you are adding from burette sodium hydroxide. So you can see that gradually pH is going up, and there's a big jump near the equivalence point, and then finally it gets all flat. That means pH doesn't change anymore because at this point neutralization happens, and we call it equivalence point. So neutralization happens means HCl completely reacts with NaOH, giving NaCl and H2O. Now, at the equivalence point or neutralization point, pH may be 7, equal to 7, less than 7, or more than 7. All depends upon the product, because product gives secondary reaction with water and can change the pH. So in this case, we have NaCl as product. So let's look at what kind of compound NaCl is. We discussed this in the past. That means we are going to discuss a quick method of finding out what kind of salt sodium chloride is. So sodium comes from sodium hydroxide, base part of it, and Cl comes from HCl. So NaOH is a strong base. We all know that. Group 1A hydroxide. HCl is a strong acid. So strong base is strong acid. Neither property is going to be dominant, so it's going to be neutral. And pH equal to 7. In other words, in this pH titration of a strong acid, strong base, equivalence point is going to happen at pH 7. But that may not be the case with other acid-base titrations. For example, if I have a weak acid and a strong base, like in this particular case, we are using this organic acid, C112 Ch, and that's reacting with sodium hydroxide, giving a sodium compound plus H2O. If you're wondering how this reaction happens, this OH reacts with H of the acid, and that's how you get H2O, and rest of the compound is formed with sodium. Now let's analyze what kind of salt we got. A salt must have an acidic end and a basic end. So this is the salt, NaC2H3O2. Now let's split that into acidic and basic end. So this Na is coming from NaOH, that's the basic end, and this is coming from acidic end. Now I'm going to attach one hydrogen. How do I know it's one hydrogen? Because sodium is plus, the other one is minus. So minus 1 means it can only grab one hydrogen, C2H3O2. So that's the acid. Now let's identify what kind of base we have. This is a strong base, group 1A hydroxide, and HC2H3O2 is a weak acid. So strong base, weak acid. So it has to be basic. So pH has to be greater than 7. What this tells us is you may neutralize a particular acid by a base, but because of the kind of salt that you get, and because of the secondary reaction with water, it can give you acidic solution, basic solution, or a neutral solution. So in the second case, because of the type of salt formed, we get a basic solution at the equivalence point. So at the equivalence point, NaOH completely neutralizes HC2H3O2. But because of the formation of the specific salt, which is NaC2H3O2, and its reaction with water, we get a basic solution. In next titration, we're looking at titration of a strong acid HCl with a weak base. Ammonia is a weak base. The product of the reaction is ammonium chloride. Again, at the equivalence point, all the HCl would be reacting with NH3. So one may think that since you completely neutralize HCl, that means it could be a neutral solution. No, just like before, the salt solution can influence the pH at the equivalence point or end point. So let's look at what kind of salt NH4Cl is. Again, we're going to split that into two halves. So let's write down NH4Cl. This part, NH4 part, acts like a metal, like calcium, sodium, like that. So ammonium hydroxide is the base part. HCl is the acidic part. And now we can identify what kind of acid we have. This is strong acid, HCl. And ammonium hydroxide is a weak base. So this is a salt of weak base and a strong acid. Obviously, acidic property dominates. So solution is going to be acidic and pH is going to be less than 7. So in problems like these, you can predict what kind of pH you'd expect at the end point or at the equivalence point by analyzing the product of the reaction. Next, we are going to discuss about pH titration of a polyprotic acid. H3PO4 is a polyprotic acid. Those of you are taking Chem 113 lab, you're going to do one such titration. H3PO4 has 3 acidic hydrogens, so it splits in three stages. In first stage, one of the hydrogens gets out, so this is Ka1, first step of ionization. H plus comes out, then you get H2PO4 minus. In second step, H2PO4 minus acts as an acid and gives off H plus and HPO4 2 minus. So that's the second step of ionization. And third step, HPO4 2 minus can also act as an acid, and that breaks down into H plus and PO4 3 minus. So that's Ka3. So by looking at different acid dissociation constants for H3PO4, we get an idea about what are the reactions that we are dealing with in a solution of phosphoric acid. So in phosphoric acid, you'd really have 3 different species, and all these can act as an acid. So you can deal with H3PO4 acting as an acid, H2PO4 acting as the second acid, HPO4 2 minus acting as the third acid. The first acid would be obviously the strongest one because you're separating one H plus from H2PO4 minus. So basically H2PO4 minus is going to attract H plus. So you're just separating H plus from a negatively charged anion. Second time, you're removing H plus from doubly negative charge, and that's harder. So in other words, there'll be smaller amount of H plus formation from H2PO4 minus. Third case is even harder than that because you're separating H plus from PO4 3 minus, and that's much harder, and that's why you have a much smaller quantity of H plus coming from HPO4 2 minus. And when you do the pH titration, the first equivalence point would be most dominant. So this is going to be most dominant. Second one would be smaller than this, even though pictorially we didn't show you that, but this would be much less visible. So first one would be quite, let me try to redraw this. It would be smaller. And third one, many of you may miss it in your experiment of Chem 112 lab. So almost everyone would miss. So first and second one would be the most visibly you'd see this rise in pH value near the equivalence point. The first one is most dominant, second one is less, third one is almost, at least the kind of pH titration we go over in the lab. Third one, I would not be surprised if most of you miss it, because third acid that comes out of H3PO4 is the weakest of all these 3 acids that you get from H3PO4. Here we're going to discuss problem number 37, page 743. This is a problem on titration. So you're supposed to predict whether the pH at the equivalence point is going to be less than 7, more than 7, or equal to 7. In order to get this answer, it's a good idea to first write down the reaction. So they're saying that sodium bicarbonate reacting with sodium hydroxide. So you're doing a titration in which you're adding sodium hydroxide to sodium bicarbonate. And keep in mind, this is a pH titration where you're keeping track of how pH is changing. And at the equivalence point, you're supposed to predict before doing an experiment whether the pH is going to be 7, less than 7, or more than 7. Okay, first write down the reaction product. It will be sodium carbonate plus H2O. You can see that this sodium, that's Na2, and it combines with CO3, that gives sodium carbonate, and H and OH gives H2O. So this is what you'd expect, these products you're going to expect at the equivalence point. Now, this particular product we need to analyze. What kind of product is this? Let's split that into acidic and basic part. Na comes from NaOH. CO3 comes from H2CO3. Or you can even say HCO3 minus. It doesn't really make a big difference. This is NaOH is the strong base, and H2CO3 is a weak acid. Keep in mind, if you know the names of strong acid, this would help you to identify which ones are weak acids. Now, strong base, weak acid. So the base, whichever is strong, that's going to be dominant. So a strong base, weak acid salt would be basic, because basic property dominates. And basic means pH greater than 7. Now let's now try part B. In part B, in this titration, ammonia is titrated with HCl. So now we need to write down the reaction between ammonia and HCl. Again, this is acid-base titration. Ammonia acts as a base, and the product is NH4Cl. So that's the product of this reaction. Now we need to identify what kind of salt ammonium chloride is. Ammonium acts like a metal, so let's identify the basic part. NH4OH, just add OH. Since ammonia is +1, so it only can have one OH. And Cl comes from HCl. HCl is a strong acid. Ammonium hydroxide is a weak base, since it's not a group 1A or 2A hydroxide. So don't misunderstand me when I said that ammonium is like a metal. It behaves like a metal, but it doesn't give you a strong base. Only group 1A, 2A hydroxides give you strong bases. But the formula was similar to sodium hydroxide. That's what I meant. So this is going to be acidic. So equivalence point is going to be acidic. pH has to be less than 7. Now in part C, titration, KOH is titrated with HBr. So let's see what kind of reaction we get. KOH, potassium hydroxide, plus HBr, giving KBr plus H2O. I hope you know what kind of compound is this. So split that into basic and acidic part, and you know that K is plus 1, so it can only have one OH, so it'd be KOH, and this would be part coming from an acid, HBr. Now identify what kind of acid you got, what kind of base you have, and so what endpoint you'd have. If it is strong acid, strong base, neither one is going to dominate, and you get pH 7. If you have one is strong and the other one weak, so strong one is going to be dominant. Here we're going to discuss about solubility equilibrium. In most of these problems, we add a substance which is slightly soluble in water. So barium sulfate is one of them. So this is barium sulfate. Only a small quantity of barium sulfate would go in water. As it goes in water, it splits into barium 2 plus and SO4 2 minus. This is how most of the time metallic compounds go in solution, by splitting into metal from the non-metal part. Equilibrium constant for solubility we write down as KSP, SP for solubility product, and is given by product concentrations on the top divided by the reactant concentration, which is barium sulfate solid. Now why did I ignore this in my expression? Because it's a solid. Remember, a solid, you'd be ignoring it. So let's forget about it and just consider it to be 1, because solid concentration does not change as long as, even if you have tiny bit of solid there. Now let's go back to our application in terms of Q value. I can have any concentration of barium 2 plus and SO4 2 minus in the solution. How? I can add barium chloride or barium nitrate, for example, and I can have sodium sulfate added to the solution. So they are going to increase concentration of barium 2 plus and SO4 2 minus in the solution. Now let's assume that I added sufficient amount of barium 2 plus salt as well as sulfate salt, sodium sulfate or potassium sulfate, so that Q value exceeds KSP value. Remember the Q value? These are any concentration, not the concentration that you'd expect at the end of a reaction. In other words, not an equilibrium. These are not equilibrium concentrations. Say Q value exceeds KSP. If that happens, we all know that Q must decrease with time, because every system will have to be going towards equilibrium. So when Q must decrease, you know that Q definition has Ba2 plus and SO4 2 minus. So if it's decreasing, that means Ba2 plus and SO4 2 minus has to decrease with time. That means reaction has to go from right to the left. What do I have on the left? A solid, barium sulfate. So that means when Q value exceeds KSP, you get solid formation or precipitate formation. What would happen is Q value is less than KSP, in the second case. Again, I can add barium 2 plus and sulfate in the solution in such a way that Q value is less than KSP. So what would happen as time goes on? Q value must increase. Remember, Q value has to eventually become equal to KSP. So Q must increase with time, and Q increasing with time means barium 2 plus and SO4 2 minus has to increase. Now, barium 2 plus increasing means reaction has to go from left to the right. That means more of the solid would go in solution in second case. So here the direction of reaction will be towards right. In first case is going to be towards left, because you're getting precipitate. Okay, so in second case solid dissolves. What would happen if Q equals to KSP? No more change would happen because it's an equilibrium. Neither additional solid would dissolve or any solid precipitate. So you already got a saturated solution. In problem 51, solubility of calcium fluoride in water is given, which is 1.24 times 10 to the negative 3. And based on this information, we need to calculate KSP, or equilibrium constant value, for calcium fluoride. This is a typical type of reaction solubility problem where you have a solid which would be partly soluble, so a part of that X is going to break down and go in solution. When it goes in solution, calcium gets separated from F minus. Now, why is X and 2X? Because from one calcium fluoride, you get one calcium and 2 fluoride. So it's 2 times more. When X is the amount that breaks down from calcium fluoride, or X amount of calcium fluoride breaks down, you get X of calcium and 2X of fluoride, because 1:1:2 reaction. So keep that in mind. And when you write down KSP expression, only the aqueous or the ions in aqueous solution would go into the expression. Calcium fluoride solid, you can leave it out, because as long as it remains as solid, its concentration is not going to change, because concentration is defined as moles per liter. So anyway, so write down equilibrium expression, calcium raised to the power 1, because this has to do with the balanced reaction, 1 calcium 2 plus and 2 F minus, and that's why you have power 2 here. Now in terms of X, calcium would be X and fluoride would be 2X. It's coming from here. So X times 2X squared, and that gives you 4X cubed. X is nothing but the solubility. That means how much of the solid has gone into the solution. And we already know that value, 1.24 times 10 to the negative 3. And finally, you get your answer. So make sure you finish this and get your final answer. This is 55A. The question is, what is the solubility of silver bromide in water? So silver bromide KSP value is given. So let's calculate its solubility. Again, I'm going to set up an expression pretty similar to what I did in last couple of problems. So we'd have silver bromide. Again, these are partly soluble substances, so only part of that would go in solution. But whenever it goes in solution, metal gets separated so that water can solvate it or surround it and keeps it in solution. That's aqueous in water solution, and Br minus aqueous. Now let's assume that initial concentration of silver bromide is A. When I just put solid in contact with water, I didn't have any silver plus or Br minus in the solution. By the time it reaches equilibrium, a part of the solid would break down, would go in water solution. So let's assume that X is the part that breaks down and go in water solution. So A minus X would be the leftover of the solid. If one silver bromide breaks down, you get one silver plus and one Br minus. If X breaks down, that gives you X of silver plus and X of Br minus. And remember, the X, the amount of solid that goes in water solution, is the solubility, because that's the maximum it can go in water solution before it reaches equilibrium. So now I can set up KSP expression, KSP, which is equilibrium constant, but since we're dealing with solubility and we call it solubility product, it'll be given by silver plus concentration times Br minus concentration raised to the power 1 because I have 1 and 1 reaction. Now I can write down in terms of x. So this is going to be x. Let's draw a line here. X times x. And on the bottom, we ignored silver bromide solid because it's a solid, so we ignore it. So basically KSP equals to x squared. So KSP is 5.0. Let's write down those numbers. 5.0 times 10 to the negative 13, and that's equals to x squared. And from here, I can calculate x value to be equal to 7.07 times 10 to the negative 7 molar. I can approximate that to 7.1 times 10 to the 7 molar. So this is the solubility. This is the amount of solid that has gone in water solution. And when it goes to water solution, it breaks down into silver plus and Br minus. So answer to this question is solubility in pure water is 7.1 times 10 to the negative 7 molar. Now we are going to do this similar problem, but slightly different from the previous problem. In this case, you already have 3.0 times 10 to the negative 2 molar silver nitrate. And we'll find out what would be the solubility of silver bromide when silver nitrate is already there. Now what does silver nitrate do? So let's just write down a simple step. So silver nitrate is a highly soluble substance in water that would break down into silver plus and NO3 minus. So basically, if I have 3.0 times 10 to the negative 2 molar silver nitrate, after it goes in solution quickly, there'll be no silver nitrate left as AgNO3. They'll be all changed to silver plus, which would be 3.0 times 10 to the negative 2, and the same amount of nitrate, which we don't care for this particular calculation. So what is most important to us is this quantity of silver plus, because that's part of this solubility problem. Now let's write down one solubility expression. Silver bromide solid that breaks down into silver plus aqueous plus Br minus aqueous. Okay. Now, initial concentration. Let's assume that I had A is the amount of silver bromide I had at the beginning. But since we already added silver nitrate, so silver plus concentration was not 0 at the beginning. It was 3.0 times 10 to the negative 2. So it was 3.0 times 10 to the negative 2. And that came from amount of silver nitrate that was added. So that's coming from here. There was no Br minus, so it's 0 at the beginning. Now, when it reaches equilibrium, part of this silver bromide would go in water solution. Let's assume that that's X, and that is solubility. So how much of silver bromide would be there left after the equilibrium? A minus X. Now keep this in mind. If X amount of silver bromide goes in solution, you get X of silver plus and X of Br minus. Now I can set up KSP expression. That's solubility product. Let's use a different color. It would be silver plus raised to the power 1, Br minus raised to the power 1, and both are aqueous. So I would have silver plus concentration, I can put down now, 3.0 times 10 to the negative 2 plus X. That's the total quantity we have at the equilibrium times X. And we already know the KSP value, which is 5.0 times 10 to the negative 13. So this number is 5.0 times 10 to the negative 13. Now we can make some approximation, which we did quite often. If X is much smaller than 3.0 times 10 to the negative 2, we can ignore that X. And this is what we end up with. That makes our calculation a lot easier. That means I don't need to solve quadratic form of the equation. So I would have, this is nothing but 0.03, 3.0 10 to the negative 3. So 0.03 X. We ignored this X, assuming that X is very small compared to 0.03. So we're assuming that addition would be same as 0.03. So now that gives you, if you do the math, let's have one more significant figures. X would be given by 1.67 times 10 to the power minus 11. I can round it off to 1.7 times 10 to the negative 11. So this is the solubility and answer to this question. So this is the molarity. So this is the solubility of silver bromide when 3.0 times 10 to the negative 2 molar of silver nitrate is present in the solution. When you compare this with our past calculation that I have shown you in last slide, in pure water, the solubility was 7.1 times 10 to the negative 7. So solubility was much larger than solubility of silver bromide in presence of silver nitrate. And it's quite understandable. We can understand it based on Le Chatelier's principle. When you have an extra amount of silver plus in the solution, equilibrium would be shifted to the left, so there'd be smaller quantity that would remain in water solution. Now here we're showing you complex ion formation between silver plus and ammonia. That's how most silver chloride goes in water solution. It forms silver amine complex. Now equilibrium constant for this kind of complex formation reaction is defined similarly. The product on the top and reactants on the bottom raised to the power coefficients of balanced reaction. So remember that K equilibrium for acidic reaction we write down Ka. For basic reaction we write down Kb. For complex formation like this we write down Kf. So complex formation helps in dissolving a substance and in separating an analysis of different compounds.